Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, so this is the lecture number 5 of Thermodynamics and Statistical Mechanics. Okay, so and also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. And also guys, please share my lecture details to your friends so that they will also be able to watch my free live lectures and will be benefited by it. Okay, so let's get started. This is the lecture number 5. So I'm going to start now. Okay, so we'll study first the slope of a diabatic and isothermal. Okay, slope of a diabatic, a diabatic, a diabatic and isothermal. Okay, slope of a diabatic and isothermal. Okay, so in case of isothermal, we know that PV equal to constant, right? And in case of a diabatic, we know PV to the power gamma equal to constant, right? So we'll differentiate it. Okay, so this is going to be P dV plus V dP is going to be equal to 0. The differentiation of coefficient constant is 0. And for this, for a diabatic case, this is going to be P, this one. This is P gamma V to the power gamma minus 1 dV plus this one V to the power gamma dP equal to 0. From here, we can get this dP upon dV, dP upon dV, that is going to be P upon V, P upon V. Okay, and that is minus P upon V. And similarly here, we'll get dP upon dV. Okay, so this is going to be minus gamma upon gamma into P upon V. Okay, well, so from here we can say the dP upon dV of a diabatic is equal to minus gamma dP upon dV isothermal, right? Isothermal. Okay, so since we know gamma is greater than 1, okay, gamma is ratio of Cp upon Cv, right? That is greater than 1. Okay, this is greater than 1. So now we can see the slope of a diabatic is gamma times the slope of isothermal, right? This is the one. Or we can write this P upon V is dV, right? So gamma into this, the minus will not be here, gamma into this, okay? Because minus P upon V is dP upon dV, okay? Well, now here we can draw the slope in PV graph. This is V and this is P. Okay, So isothermal curve is going to be like this, and a diabatic is going to be like this. Okay, so this is isothermal, and this is a diabatic, a diabatic, okay. These are the graph in PV graph. So clearly we can see that slope of a diabatic, slope of a diabatic, slope of a diabatic is greater than slope of isothermal. Slope of isothermal, okay, because we can see slope of a diabatic is gamma times slope of isothermal, right? And this is the graph of a diabetic, and this is the graph of isothermal. Okay, so you can see clearly this is more steeper, right? So slope of a diabetic is greater than slope of isothermal. Okay, next is quasi-static process. Okay, quasi-static process, quasi-static process, quasi-static process. Quasi-static process. Okay, so what is quasi-static process, guys? This is very slow process. Okay, infinitesimally slow process. Okay, so very slow process, very slow process, in which at every point of the process, okay, so very slow process in which at every point of the process, every point of the process, every point of the process, the system is in thermodynamic equilibrium, in thermodynamic equilibrium. Okay, so very slow process. Okay, very slow process in which at every point of the process the system is in thermodynamic equilibrium. So the process at every point of the process the system will be in thermodynamic equilibrium, and that is called quasi-static process. Okay, so that implies, so at every point P1 is going to be equal to P2, okay, and T1 is going to be equal to T2, and mu1 is going to be equal to mu2. Okay, so this is the quasi-static process. So at every point of the system, every point of the process of the system, okay, the system will be in thermodynamic equilibrium. At every point the system will be in thermodynamic equilibrium, okay, in quasi-static process. Next is reversible process. Reversible process. So what is reversible process, guys? Okay, very important. At any process that can be taken through the same path reversibly. Okay, so any process any process that can be any process that can be taken through any process that can be taken through the same path reversibly. Okay, so this is called reversible process. So any process that can be taken through the same path reversibly. Okay, so but okay, so like this is PV graph, P and P, right? And this is the process from A to B. It is going from A to B. So this process, right? Any process that can be taken through the same path reversibly. Okay, A to B and B to A, right? So this is the if it is so any process that can be taken through the same path reversibly, that is called reversible process. This process is reversible process. But in practical, guys, all processes are irreversible process in nature. Okay, all processes all processes are irreversible irreversible all processes are irreversible in nature. Okay, so this is the reversible process, guys. Next is second law of thermodynamics, guys. Okay, second law of thermodynamics, very important, guys. Okay, second law of thermodynamics. Meanwhile, let me just check whether I'm audible or not. Okay, so this is yes, I'm audible, so I'll proceed further. Okay, so now this is second law of thermodynamics. So I'll write some point for second law of thermodynamics. Okay, so heat, we know that. Okay, heat always flows heat always flows from high temperature heat always flows from high temperature to low temperature to low temperature. Okay, so heat always flows from high temperature to low temperature. Okay, like the current always flows from high potential to low potential. Okay, and second point is heat energy can be transferred heat energy can be transferred heat energy can be transferred in mechanical energy. Okay, in mechanical energy, and vice versa Okay, so this is heat energy can be transferred in mechanical energy and vice versa. Okay, vice versa. Okay, next point is this is the second these are the points of second law of thermodynamics. Okay, so I will make a figure as well here. Okay, so this is the piston here. Okay, it goes here. Here in this case, you can see if T increases, okay, we will decrease, okay, decrease, okay. So we have increased temperature and position area, and we can see because of increasing temperature, V decreases, okay, and in this case, T increases and we can see internal energy increase, okay. T increases means internal energy increases, okay, and so we have increased the temperature, we have and decreased the volume got decreased, okay. So volume decreased, we have decreased the volume from there to this, and temperature is increased, okay. So now we are going to study the heat engine, right? Very important, heat engine. Heat engine, okay, heat engine. Heat engine, okay, so I'll draw the diagram. This is the source, guys, okay, this is the source, this is working substance, this is working substance, okay, and this is sink, and the source is at temperature T1, guys, okay, and sink is at temperature T2. So we have extracted Q1 heat from the source, okay. So what happen is then W work is done, okay, W work is done, that is output, okay. W work is done here. We have taken Q1 heat, we have extracted Q1 heat from the source. W work is done, and remaining heat, that is Q2, goes to the sink, okay. This goes to the sink, Q2, okay. So this is the source. Q1 heat we have taken from the source, and W is used for work done, okay. Remaining Q2 heat goes to sink, okay. So now we'll find efficiency, okay. So efficiency is going to be, this is input, right, okay, input. So here efficiency eta is going to be, that is output upon input, okay. So this is the efficiency, okay. So eta is going to be, what is output? Output is W, right? Output is W upon Q1. This is the efficiency, guys. Very important formula, okay, for heat engine. Next, here, or we can write eta, because we know here we know that Q1 is equal to W plus Q2, right? Q1 heat extracted from the source, W is used for work done, right? And remaining Q2 heat goes to sink, right? So Q1 equal to W plus Q2, right? So from here we can find the value of W is going to be Q1 minus Q2, okay. So we'll put the value of W in eta here, eta. So this eta is going to be Q1 minus Q2 upon W. My apologies, Q1. Okay. Now eta is going to be equal to Q1 in this 1 minus Q2 upon Q1. Okay, so this is the value of eta. Eta equal to 1 minus Q2 upon Q1. Okay, this is the value of eta, very important. This is the efficiency of the heat engine. Okay, important formula. Now we are going to study Carnot cycle. Okay, Carnot cycle. Carnot cycle. Carnot cycle. Okay, so this is reversible cycle, guys. Okay, reversible. Carnot cycle is reversible cycle. It is reversible cycle. Okay, so reversible cycle. Okay, so a Carnot cycle is a reversible process, right? Cyclic process. Since it's a cyclic process. Okay, Carnot cycle is cyclic process, and we know in cyclic process, in cyclic process, delta U equal to 0, right? So I'll make a diagram, Carnot cycle in PV. So this is P and this is V. Okay, so here I'm going to make a Carnot cycle. These are isotherm. Okay, okay, so this is A, this is B, this is C, and this is D. Okay, so it's a cycle process, Carnot cycles. First we go from A to B, then B to C, C to D, and D to A. Okay, so this is the isothermal expansion, guys, because in this case volume is increasing, right? So this is isothermal expansion, and this is adiabatic, right? And this is isothermal compression. Okay, and this is adiabatic, the ABC is adiabatic expansion, and this is adiabatic compression. Okay, so we have made some mistake in the diagram. Let me just correct it. This one. Okay, this is D, this is C. Okay, okay, so this one. So this is adiabatic, BC is adiabatic expansion, this is adiabatic compression, this is isothermal compression, because volume is decreasing. Here also volume decreasing, here volume increasing. Okay, now it is correct figure. Okay, so now we'll explain curve one by one. Okay, so first AB curve. Okay, from A to B, this is from A to B, so this is isothermal expansion. Okay, this because this is volume is expanding isothermally, right? So isothermal expansion. Isothermal expansion. And isothermal expansion, we know that is Q1 is going to be the total heat. Okay, in isothermal expansion, that is work done for Q1 is going to be nRT1 ln VB upon VA. Okay, so this is nRT1 ln VB upon VA, right? This one, VB upon VA. We know the formula for isothermal, like nRT ln V2 upon V1, right? So we are going from A to B, so VB upon VA, right? This one. And now this is equation number 1, important one. Okay, next from B to C, second is B to C, that is adiabatic expansion, right? This one, B to C, adiabatic expansion. Adiabatic expansion. Okay, B to C, adiabatic expansion. And adiabatic, in adiabatic expansion, we know the formula, right? So there is a formula, that is T2 V d to the power gamma minus 1 equal to T1 V8A to the power gamma minus 1, right? That is T V to the power gamma minus 1 equal to constant we have used. Okay, so T2 from here, right? T2 Vd gamma minus 1, this is T2 and this is Vd, now this is Vb, this is Vb. Okay, this is Vb, T2 Vb gamma minus 1, this one, T2 Vb gamma minus 1. B to C. Okay, yes, I made mistake. So this is going to be this is going to be this one, T1 Vb gamma minus 1 equal to T2 Vc gamma minus 1. This is the one, guys. This one, B to C, right? So T1 Vb gamma minus 1, T2 Vc gamma minus 1. Okay, this is equation number 2. Because we know Tv to the power gamma minus 1 equal to constant in a diabatic process, right? Next is from D to A, that is C to A, this one, C to A, C to D, my apologies, C to D, okay. C to D is going to be it's an isothermal process, right? C to A, C to D, C to D is isothermal process, right? C to D. So this is isothermal compression, right? C to D is isothermal compression, this one. So Q2 is going to be here, Q2 is going to be this one, minus nRT2 ln Vd upon Vc. Okay, this is equation number 3, Q2, right? Because minus we have taken because here the volume is decreasing. Okay, it is the case of isothermal compression. Now next is D2A. D2A is adiabatic compression. Okay, adiabatic compression. Okay, D2A. So this is going to be, this is T2 Vd to the power gamma minus 1 equal to this is T1, guys. T1, and this is going to be equal to T2 Va to the power gamma minus 1. Okay. T1 Vd to the power gamma minus 1 equal to this one. T1 Vd, because we are going D2A. T1 Vd gamma Vd T1, this is T1 V to the, and these isothermal curve, right? This is at T1 and this is at T2. Just give me 1 second, guys. Okay, just give me 1 second. Just give me 1 second. Okay, guys. So these are the this is the in DA. This is adiabatic compression, right? This is equation number 4. Okay. So now what we are going to do is from this is 4. Now from equation, what we will do is equation 2 by 4. Okay. This is equation 1. This one. This is equation 1, equation 2, equation 3, and equation 4, right? So what we are going to do is this one. Equation 2 by 4. Okay, equation 2 by 4. So this one is equation 2 by 4, right? So this is going to be if you do T2 by 4, so this equation is going to be T2 Vd to the power gamma minus 1. My apologies. So this is going to be this one, Vc upon Vd. Vc upon Vd is going to be Vb upon V. Okay, this one. This you can say equation number 5. And also, and we have Q1 is equal to nRT nRT1 ln Vb upon Va, right? This one. This is equation number 5. And Q2 is we have this one. We can write the Q2 is going to be that we have this one, right? I'll show you. Q2 nRT. Now I'm going to, so by log property I'm going to remove this sign minus, so this I'll write log Vc upon Vd, right? So this Q2 is going to be plus nRT2 ln Vc upon Vd. Okay, so it was here, it was this one. Here it was Vd upon Vc, right? So this became Vc upon Vd. So now this implies Q1, so this is 6, okay? So we are going to do 5 by 6, okay? So this Q1 upon Q2 is going to be this one, T1 upon T2, because we can see from this, from equation 5, Vc upon Vd equal to Vb upon Va, okay? So this value is going to be 1. So this is very important result, guys, okay? This is very important result, you need to note down. So this is Q1 upon Q2 equal to T1 upon T2, okay? Well, next is, or we can write, so now we have a formula of efficiency, right? Eta equal to 1 minus Q2 upon Q1, Q2 upon Q1, right? So, or we can write 1 minus Q2 upon T1, okay? This is important, very important formula, guys, you need to note down, okay? So, from Carnot cycle, what we have found is Q1 upon Q2 equal to T1 upon T2, right? So, this means 1 eta equal to 1 minus Q2 upon Q1 equal to 1 minus T2 upon T1. Okay, guys, so this is the one. Now I will solve one question also, okay? Meanwhile, just give me 1 second, guys. I'm just checking something. This one, yeah. Okay. Okay, guys, it's correct. Well, next I'm going to solve one question. Question is, a Carnot engine is operated between two reservoirs at temperature of 450 Kelvin, and 350 Kelvin. Okay. If the engine receives, if the engine receives 100,000 calories, 1000 calories of heat, 1000 calories of heat from the source, okay, in each cycle, calculate the amount of heat rejected to the sink in each cycle. Okay, so this is the question, guys. Question is, a Carnot engine is operated between two reservoirs at temperature. So there is a Carnot engine which is operated between two reservoirs which are at temperature 450 Kelvin and 350 Kelvin. Okay, if the engine receives 1000 calories of heat from the source in each cycle. Okay, in each cycle, they calculate the amount of heat rejected to the sink in each cycle. Okay, that's what you need to find out. Each cycle. Okay, options are given. Option number A is 3.33, calorie. Option B is 555.55 calorie. Option C is 777.77 calorie, and option D is 999.99 calorie. Okay, so this is the question, guys. Very good question, and I'm going to solve it using Carnot cycle. Okay, so Carnot cycle is operated between two reservoirs at temperature 450 and 350. Okay, if the engine receives 100 calories of heat from the source in each cycle, we calculate the amount of heat rejected to the sink. Okay, Q2 we need to find out. So we have a formula, guys, which I have derived in Carnot cycle. This is Q1 Q2 equal to T1 T2. Okay, so this formula I'm going to use. Okay, so since we know Q2 upon Q1 equal to T2 upon T2, right? This is same thing, guys. This one Q1 Q2 equal to T1 T2, or we can write Q2 upon Q1 equal to T2 upon T1. Okay, so this is in for the Carnot cycle, right? And we need to find Q2. Q1 is given, and since Q1 is given in the question, right? So that is given 100 calorie. Sorry, 1000 calorie, right? And T1 is given, guys. T1 is given this 450 calorie, 450 Kelvin, and T2 is given, guys, that is 350 Kelvin, right? So from here, Q2 is going to be Q2. We need to find out. It's a formula based question, right? So Q2 is going to be Q1 T2 upon T1, right? So this is going to be 1000 into T2. Here, yeah, T2 is 350. 350 upon T1 is 450, right? So this value is going to be 777.7 calories. So this much of heat is rejected to the sink. Okay, so this is the answer, guys. This will get cancelled with this. Okay, so this is the answer, and also we can if we have been asked to find out the efficiency and work done, we can also find out. Okay, if we have been asked to find out the work done, W, and W we know, right, that is Q2 minus Q1. Okay, so W is going to be Q2, we have this one, and Q1 is this, so this is 1000 minus 777.7, right? So this value is going to be 223.23 if a work done is asked, okay, in the question. And or if efficiency is asked in the question, then efficiency we know that is efficiency is equal to 1 upon Q2 minus Q1, right? Or this is going to be 1 minus Q2 is or we can write 1 minus T2 upon T1, right? Because Q2 upon Q1 equal to T2 upon T1 in Carnot cycle, right? So that is going to be 1 minus T2 we have been given, that is 350 upon 450. 0, 0 will get cancelled and this value is going to be 2.9, or we can write in percentage. So this is going to be 2.9 or equal to 22%. Okay, so this is the different value. So we can find out easily that eta or work done. Okay, right. So this is the question, guys. Next is refrigerator. So we are going to study about refrigerator. Okay, refrigerators. Okay, refrigerator. Okay, so I'll explain the work, how it works. Okay, so guys, this is the source. This is the refrigerator and this is the sink. Okay, sink, source. And this will be at temperature T1. Okay, this is low temperature, guys. Okay, low temperature. And sink will be at T2. This is at high temperature. High temperature. Okay, and this is refrigerator. Okay, and here we can see here T2 is greater than T1. In this case, we have seen T2 is here. In this case, in case of heat engine, here T1 is greater than T2, guys. Right. So, but if we talk about this refrigerator, T2 will be greater than T1. Okay, and in case of refrigerator, so this is at low temperature. Okay, and this is the refrigerator, or in case of this refrigerator, this is high temperature, right? Q1 plus W, that is going to be equal to Q2. Okay, so this is Q1 and this is Q2. Okay, so Q1 plus W is going to be equal to Q2. Okay, this is the one, and so from here W is going to be Q1 minus Q2. In case of heat engine, we have seen W equal to Q2 minus Q1, right? In case of refrigerator, this is W equal to Q1 minus Q2, or Q1 plus W is equal to Q2. Okay, and so now in case of refrigerator, the efficiency is going to be, or we can write coefficient of performance, it is called coefficient of performance. Coefficient of performance K, that is going to be equal to output upon input. Okay, so that is the Q1 upon W. In case of heat engine, that was the eta equal to W upon Q1, right? So this is W1 upon sorry, Q1 upon W. So that is going to be, here we can write, the value is going to be mod Q1 upon W is Q2 minus Q1. Q2 minus Q1 in case of refrigerator. Okay, Q2 minus Q1, or we can write in case of refrigerator T mod of T1 upon T2 minus T1 mod T2 minus T1. Okay, so this is about the refrigerator. Okay, so this is the K. In case of refrigerator, this is called coefficient of performance. Okay, and that is denoted by K, and K is going to be equal to Q1 upon W. And in case of that heat engine, we have seen efficiency eta is equal to W upon Q1. I'll show you here. W upon Q1. Okay, output upon input, right? And here this is Q1 upon Q2, right? So this is the input, guys. Here in case of this one, high temperature refrigerator is input. This is W. Okay, this is input, and the Q1 heat, this is output, Q1 upon W. Okay, guys. Well, so guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. And also I would request you guys, please share my lecture details to your friends, so that they will also be able to watch my free live lectures and they will be also benefited by it. Okay guys, so I'm going to stop here. Okay guys, thank you so much. Bye now.